Hi everyone, welcome for today's class. Today we will do second lesson from Electromagnetic Induction, class 12. In the previous lesson, in the first lesson, we have discussed Faraday's experiments and Faraday's laws of electromagnetic induction and Lenz's law. So you already know what is induced EMF, how it is produced. Induced EMF or induced current is produced when the magnetic flux linked with a conductor or circuit changes. Okay, today we will discuss about an important concept called motional EMF. You consider a conductor moving through a magnetic field. If it is moving, suppose it is moving perpendicular to a magnetic field. So what will happen? Magnetic flux linked with it changes. So an EMF is induced across it. This EMF is due to the motion of the conductor. That is why it is called motional EMF. Let us find the equation for the motional EMF. So you are considering a conductor moving through a uniform magnetic field. Suppose the magnetic field is directed into the plane of the paper. I will show you in the diagram. See, in this region, a uniform magnetic field is directed into the plane of the paper. This into mark means magnetic field directed perpendicular to the plane of your whiteboard. Okay, directed inwards. Now you consider a conductor or you consider a rectangular loop. This is a rectangular wire frame I am considering. Rectangular wire frame. Now you can move a conductor. This is a conductor. I name it as AB. AB. Okay. This and C, this is D. Suppose the length of the conductor is L. Okay. As you move the conductor, suppose you move the conductor in this way with a velocity V. See, when you move the conductor, after some time, the conductor will be reaching here. So it sweeps an area. Suppose that distance moved is X. It sweeps an area. So magnetic field is there. The conductor is sweeping an area. So magnetic flux is changing as it is moving. You can find out the magnetic flux. Okay. What is the equation for magnetic flux? Phi is equal to B into A. B is here constant. A is, the length of the conductor you take as L, breadth, that distance moved. You see this rectangle area between the conductor and the dotted line I showed. The dotted line, that conductor is after some time, it is moving through a distance X. So BLX. Now, you can find out induced EMF by applying Faraday's law. What is Faraday's law? Induced EMF is minus d phi by dt. So minus of d by dt into BLX. Here B is constant, L is constant. Take out BL into minus dx by dt. But minus dx by dt, dx by dt is velocity. We put minus dx by dt as velocity. Why this minus sign? We already discussed. Induced EMF has an opposing nature. That is why the minus is coming. So E is equal to what we can write? BLV. So this is the equation for the motional EMF. E is equal to BLV. So motional EMF is the induced EMF developed in a conductor when it is moving through a magnetic field. It is due to the motion of the conductor. That is why the name motional EMF. And the same equation we can obtain using Lorentz force also. So next I show this by Lorentz force. Okay. See, when I suppose there is a charge on the conductor, this is a charge on the conductor, suppose positive charge. So when the conductor is moving, the charge is also moving, right? When the charge moves through a conductor, it experiences a force, magnetic force on a moving charge. That is F is equal to Q into V cross B. Okay, the magnetic force on the charge. So when the conductor is moving, I am considering a charge. I mark there at the plus sign. The charge also moving. So when charge moves through a magnetic field, it experiences a force given by F magnetic is equal to Q into V cross B. Is equal to QVB sine theta. Here magnetic field is perpendicular to the conductor. So theta is 90 degree. Okay. So we can write F magnetic is equal to QVB. So now what is the direction of this force? You have to apply Fleming's left hand rule. Magnetic field is into the plane of the paper. So magnetic field is represented by forefinger. Central finger charge movement is represented by the thumb. So thumb is pointing left. Then current will be in the upward direction. Forefinger represents the current. So positive charge move in this way, right? So current, so there will be a current, right? Positive charge moves in this way from A to B. Now we can calculate the work done. EMF is work done by charge only. So work done when the charge moves through a distance. Distance L. So it is moving across the conductor from A to B. So length of the conductor is L. So work done W is equal to force into displacement L. So QVBL. Now you know the equation for EMF. What is EMF? For potential difference. EMF is potential difference only. EMF, you know the equation, work by charge, W by Q. So QVBL divided by Q. You can cancel Q. So what is the induced motional EMF now? BLV. So we obtain the equation for motional EMF by invoking Lorentz force. F is equal to M into Q into V cross B. This is known as Lorentz force. What is Lorentz force? It is the force acting on a magnetic field, force acting on a charge when it is moving through combined electric and magnetic fields. That is the definition for Lorentz force. Okay. So what is the equation for Lorentz induced motional EMF? BLV. One more thing, here there is an electric field also. See, listen, I am drawing the conductor AB separately. here on the left side. So this was the positive charge. And I explained you, when the conductor is moving towards left, the charge experiences a force upward. So what will happen? Positive charge moves up. That means positive charge will be accumulated on the top end. And then negative charge will be accumulated on the lower end. So there is a potential difference, or there is an electric field. Okay, there is a force due to this electric field also. This electric field direction is in this way. Okay, so on the charge, there are two forces. First of all, this is the charge I am writing on single charge on the conductor. Force due to magnetic force is in this way, upward, but electric force is downward, right? They are equal and opposite. So this magnetic and electric forces on the charge is equal and opposite, so they cancel out. Okay, so this charge on the conductor will not experience a net force. Okay. So we derived the equation for motional EMF. E is equal to BLV. Now we can find the equation for the power produced. You know, induced current you can calculate. Induced current I equals E by resistance of the conductor. So BLV by R. This is equation for current. Then power equals E into I. I is BLV by R. Okay. Into E is BLV. So what will be the equation? V square L square V square by R. This is the equation for the power. Okay. This power is lost as heat in the conductor. You know, when the induced current passes through the conductor, due to the resistance, heat is developed. Okay. So power is V square L square V square by R. Now, this power, who is producing this power? From where does this power is coming? You know, we have to move the conductor to get this induced EMF. So external agency is doing the work there. Okay. Here also, you know, law of conservation of energy, the mechanical work done, converted into electrical energy. So the source of this power is the external agency who is moving the conductor. Okay. This is the converted into electrical energy. Now, if you can find out the mechanical power in another way. You know, when the conductor is moved through a magnetic field, it experiences a force. That force, you know, V L sin theta, theta 90 degree. Then power can be written as F into V also. So VIL into V. But I is BLV by R. I is BLV by R into V. So you are getting B square L square V square by R. So this is the mechanical power. So in the previous equation, that power is converted into heat, right? Heat energy. Power loss due to heat energy. Now the mechanical power. See, we are moving the conductor through the magnetic field. When the conductor through a magnetic field, force on it is BIL. So we can find out the power. Power, another equation, force into velocity. So you will get the same equation. Okay. This topic is very important for the examination point.